All right, I'm going to go through the constant speed or constant velocity worksheet so that we can understand all this stuff. Uh, Appreciate those of you guys that met with me one-on-one because I think that's a bigger help than going through this, but we'll do the best we can. So the first thing you had to do, make a position versus time or distance versus time graph that shows motion with constant velocity, starts at a position of 10 meters at time 0 and ends at a position of 30 meters 20 seconds later. The object then stays still for 15 seconds. So I give you the hint to graph 3 points and put that graph in there. So what you had to think about is what are the 3 points that I'm graphing? And so if you do that, we're making a basically time and distance or time and position. So my first point at time 0 is at a position of 10 meters. So if I'm thinking XY coordinates, that's the first spot. And then the second one is at a time of 20 seconds, the object has moved to a position of 30 meters. And lastly, the object stayed there for 15 seconds. So at a time of 35, it's still at a position of 30. So those are my 3 points that I'm looking at graphing. And so I've already put those into a spreadsheet right here. So I went to Google Sheets and I just made my columns time and distance, and I put in those 3 points. So then to make the graph, I just highlight those, go to Insert, Chart, and boom, it puts my graph in there really easily. And some of us struggle with, we keep putting time on the y-axis, and we can't do that. Now, I did know some of you guys had a graph like this that cuts off right here. So it's a pretty easy fix to be able to have it so it shows that line. So if you go to the chart editor, which pops up when you make this, and you go to Customize, and what we want to customize is our y-axis here, so our vertical axis. So I click on vertical axis, I scroll down, and it just has here for a maximum value. So I can just put 40 in, and then boom, it just makes my graph a little nicer to read. So I've got my graph made there. Click those 3 dots. I want to copy the chart, go back to my worksheet, and then I'm going to right click here and I'm going to paste. I want to link it to the spreadsheet, and boom, puts my graph in there. So I'm good to go with doing that. So that's how your graph should look for question number 1. If you hand drew it, some of you did, and that looked good. So I think it's easier to do on Google Sheets. But so question 2 then, and I worded it specifically like this because it's strange, and that's the way some stuff gets worded in physics. So I kind of want you guys exposed to that a little bit. So it says, what is the rate of position change for the first 20 seconds from this graph? And what that's really asking, rate of position change, is just a fancy way of saying average speed. And so we also know by this point that the average speed from a distance time graph is equal to the slope of this line. So I have a couple different things that can happen in my brain to help me answer this question. I can think of the slope. I can think of what's the position change here, the change in y over change in x. And so my change in y is 20 meters. Now, some of you guys did 30 because you knew it was at 30, but the key for this is that it starts at a position of 10. So its position change, how much distance it traveled here, was a total of 20 meters. And it did that in 20 seconds. And so if you get your calculator out and you punch that in, 20 divided by 20, you might have to use your toes, but that is 1 meter per second. So that's all that's asking. And so it's asking really, this is saying, what was my average speed, which I know is constant because this is linear, what was my speed during that 20 seconds? And that's 1 meter per second. That helps us down here with this next set of questions, which were also kind of hard for us too. So what we've got to think about when we do number 3, a couple of things. One, these first 2 ask for how far. So any time right now where I'm asked how far, I know that distance equals speed times the time. So that equation, or velocity times time, either one, it doesn't really matter for us. So how far had the object moved after the first 5 seconds? So what some people did is they went to the graph here and they said, okay, this is about 5, this is 15. So they incorrectly answered 15. And if I had said what's the position after 5 seconds, 15 would be the right answer. But because it's just how far it had it moved, you have to think, okay, how fast is it going and for how long? That's my velocity and my time. So if it's going a velocity during this first part of it, it's going 1 meter per second. We already figured that out. So if it's going 1 meter per second for 5 seconds, then this has gone 5 meters. After the first 10 seconds, so it's gone 1 meter per second for 10 seconds, so that's 10 meters. You could also do that if you didn't want to do the math. You could look at, okay, here's 5 seconds and 15, so 15 from 10 is 5 meters. Or here's 10 seconds, it's at a position of 20, so it has gone 10 meters. So that's the same thing. Really, the math is just a fast version of it. Now, average speed, so we talked about this in class today, but when you see average speed, you know that you have this equation, that the average speed or average velocity equals distance divided by time. So it's for the whole trip now, so for the whole time. So you have to think, how far did I move? And I moved 20 meters. And how long was the whole trip? Well, it was 35 seconds. So to do that, I would do 20 meters divided by 35 seconds. And that equals, I think it was 0.57 if I remember right. But let me just punch that in to just double check. 20 divided by 35, 0.57. So 0.57 meters per second. And one thing that happened with a lot of kids during this is that they messed up the units. So we want to make sure that our units are correct. I can do that same thing with average speed for the first 10 seconds. I do distance over time. So in 10 seconds, I had moved 10 meters divided by 10 seconds. So this was 10 meters divided by 10 seconds, and that equals 1 meter per second. Average speed for the first 30 seconds. So I had moved 20 meters in that first 30 seconds. So this is just 20 meters divided by 30 seconds. 2 divided by 3 is 0.67 meters per second. So that leaves us just with 2, which are instantaneous speed. And the way you're going to find those instantaneous speed, that's the speed at any point. So like right at 10 seconds, how fast am I going? Or right at 30 seconds. And so I got to use the clues from my graph or what the problem tells me. And I know this line tells me I'm going a constant speed of 1 meter per second. So at any point on there, so at 10 seconds here, I'm going 1 meter per second. So that's my instantaneous speed at 1 meter per, or at 10 seconds, is 1 meter per second. Then the object gets here and then it stops moving. And you knew that, we said that in the question here, it stays still for 15 seconds. So if I'm staying still, then I'm not moving, so my speed is 0. So I can also tell that because that's the slope of this line. Up here, it has a slope of 0, so I'm going 0 meters per second. So that's how I would solve number 3. I get down to number 4, and this causes some confusion, which is fine, right? And we just got to figure it out. And so what you got to think about is relative to each different object that the question talks about. So if I'm in a bus going one way, and you're in a bus going the other way, relative to me, one of the easier ways I found in telling kids this is, so here's the buses right next to each other. The bus I'm in goes 20 meters in 1 second. The bus that someone else is in goes 30 meters the other way. So after 1 second, they're 50 meters apart, right? They were right next to each other. They were passing. 20 meters, one bus moves 30 meters the other way. So 1 second later, they're 50 meters apart. So that's one way of thinking that from your perspective or relative to you, the other bus seems to be moving 50 meters per second. That's because you're going opposite directions. It would be a different problem if you guys were both going the same direction. B says, how fast does your bus seem to be moving from the other bus's point of view? And so I like this because this really gets us at the relative motion idea. Because someone else on the other bus, you move 20, they move 30, they still think that you're moving 50 meters per second, or you're moving 50 meters per second relative to them. And so the answer for B is the same as A. It's still 50 meters per second. So if you can understand that, you know that motion relative to you, they were moving 50 meters per second, but relative to them, you were moving 50 meters per second. So it's kind of neat to think about both of those perspectives. It would be like if I was walking across the room and you were sitting there, you could say, I'm moving 5 meters per second, and I could look at you and say, no, you're moving 5 meters per second, right? So then here, how fast does the other bus seem to be moving from the point of view of a person standing by the road? So the other bus is the one going 30 meters per second. So if I'm standing there, the bus drives by at 30 meters per second, it appears to be moving at 30 meters per second. So no different. Just like if you were standing there watching cars go by and one went by at 50 miles per hour, it would go by at, relative to you, 50 miles per hour. So that was that set of questions right there. And then I put a page break in here so I know that this moved these down. Now, what I found with these, and I'll put all the answers in a minute, but really beneficial, and most of you guys did a great job of this, of showing the equation. The reason being is because some of these you can do in your head, no problem. But getting used to writing the equation and solving it that way is just really beneficial to you guys for this class. So it takes a little bit more work, but I don't think it takes really more than, maybe 10 seconds per problem. So I think that's worth it. And so what I might suggest is when you get to this, so we're doing just velocity equation one. So we know that velocity equals distance divided by time. And then rearranging those equations or using that triangle, we know distance equals velocity times the time. And then time is going to equal, time would equal distance divided by velocity. So these are really the three equations that I would use in doing any of these problems. And so it's a matter of looking at what it's asking. So like this one asks, what's my speed or velocity? So I know I'm going to use this equation there. So I might copy and paste that there so I know what to use. Here's another speed one. So I'm using that equation again. Here's a speed one, that same equation. So I'm going to go through and do this and put the answers up, and then I'll come back. I'm going to pause it though. Okay, so we're back. So I just went through and put all the equations in. Anytime it was speed, I put in the velocity equation. Anytime it was distance, I solved it that way. And so a couple mistakes that people made on here. One was this one was 2 city blocks, so the distance was really 160. Not a big deal if you miss that and you had done it as 80 meters in 32 seconds. So people inverted this last one, so I'm not sure why that was. Maybe just going fast or something, or it's the last problem, so we're a little sloppy. If a bird getting from Holt to East Lansing in 8 seconds was pretty fast for you, I agree. That is a amazing bird. But that's what it looks like. I'll also post just the key in the classwork stream. But hopefully this helps some of you who maybe didn't have time to meet with me one-on-one. And looking forward to seeing you guys next time.